Thank you for inviting me. It's a great honor to be invited to celebrate Eli's achievements. I had a similar bash myself a few years ago, which was very enjoyable. I hope similarly enjoyable for you, Eli. Though as a Bell Labs, ex-Bell Labs employee like myself, you can at some stage expect a roasting, I expect. Those who've been at Bell Labs know what a roasting is. So I guess Eli and I have a common theme in our research, which can be summarized by function through structure. And indeed, it was Eli's work that inspired me to start along this line. This is how I got into the photonics game, and this is one of Eli's very famous papers, perhaps the most famous paper, certainly the most cited one. And here's the key bit here. Three-dimensional periodic dielectric structure has an electromagnetic band gap which overlaps the electronic band edge, then spontaneous emission can be rigorously forbidden. And Eli and I have a background in electronic band structure, so that was a concept which came naturally to us, and but it was a revolution to the optics community, who thought of things like spontaneous emission rates as a God-given constant of nature and not something that mere man could fool around with. So this idea of structuring the density of states through a photonic structured periodic medium was revolutionary to them. And many of the ideas which have impact in science, I think, are ideas which are actually carried across from one field to another, and that's something I learned during my time in science. However, there was a problem, and the problem is that with most materials that form these structures which are periodic on the right sort of scale, like butterfly wings, the Bragg scattering, the band gaps you get, repels light only in certain restricted angles. So to get a complete band gap so that wherever you tried to get into this solid, you were reflected, wasn't possible. So in nature we see these structures, but they have nice colors, but there's no absolute band gap. And indeed, the famous curmudgeon who headed up Nature magazine, John Maggots, for many years, had a go at Eli over this, and he wrote this article in News and Views called "Photonic Band Gaps Bite the Dust." So eat your heart out, Eli. And, but he did concede that it was a radical idea. If only it were possible, this has been quoted many times, to make dielectric materials, blah, 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 almost magical things will be possible. For example, possible to embed materials such as atoms and molecules at excited states incapable of getting rid of their excess energy. And I like to illustrate this by the fact that if you struck a match in these, you could not strike a match inside these structures because it couldn't emit its radiation into them. And that's a sort of dramatic way of conveying the idea. But unfortunately, John Maddox couldn't conclude his article on a positive note. He concluded that really this was too great a challenge, but not for Eli. So here comes Yablonovite, and I don't know how many samples, how many drill bits you ruined trying to make these samples, Eli, but this, after many trials, Eli and his team succeeded in making a structure which at microwave frequencies, at any rate, had a complete band gap. So however you tried to shine light into this structure, it always bounced back, and that meant there was no density of states inside the structure. And this now famous structure, which involves the entry of the 3 drill bits through the same hole, creating the threefold axis of a cubic structure, is now famous and reignited the fire about that concept of a photonic insulator. And I was given the job by Maddox's successor of writing a News and Views article on this and helping getting the message to the world that this mysterious quantity, the photonic insulator, finally been created. And that certainly inspired me to get into the game of optics. I came with the arrogance of an electronic structure man, thinking it would all be easy, and soon discovered that although it wasn't easy, it was certainly challenging. And the amazing thing, I think, is how much fundamental optics there still is to do, even though the ground rules were laid down by Maxwell much more than 100 years ago. And it's certainly been a good ride for me, and so I thank Eli for that. So now I want to tell you a little bit about the recent things we've been doing in London, which have this theme of structure, function through structure. And the theme I'm going to take is harvesting light. What do I mean by that? Well, it's related to the previous talk, how we gather light and bring it to where we want it to be. So in contrast to focusing, which you do with a lens, which point by point relates an object to an image, a harvester is a much cruder device. It concentrates everything to a single point. It just grabs it wherever it's coming from, directs it to a single point. And that's what you do in photosynthesis. You harvest light over a large area comparable with a wavelength or greater, and then concentrate the light through the first mechanism, in that case, through the near field, to the very small scale where the chemistry happens. So as often in optics, there's a clash of length scale, that light is really very big stuff. The wavelength is of the order of a micron, and often the things you want it to interact with are a couple of orders of magnitude smaller than that, certainly in case of molecules. So we might want to do things like make very intense concentrations of light, forcing photons to interact with one another, enhanced nonlinear processes, which are normally very weak. Or we might want to go for this goal of single molecule sensitivity, again, by collapsing that length scale between the wavelength and the molecule. Might enhance the efficiency of solar cells, though in this company I won't have the cheek to say anything about that. And possibly improving the efficiency of lasers. And of course, just like focusing, harvesting suffers from the same restriction if you involved conventional technology using lenses and ray optics, which are limited to focusing down to the wavelength of light. If you want to do better than that, you've got to do something else, which in my case will be plasmonics. So here's the idea. A typical structure might be two closely spaced cylinders or spheres. They, as I'll show, will harvest the light, and then in this region of concentration here, you can perhaps place some nonlinear material, or if these cylinders are made of gold, they have a natural Chi2 at the surface, which is quite big, but not big enough to work very well unless you enhance the light. And so you can imagine putting two frequencies in and getting two frequencies out. Of course, if you want to do that, then this can't be narrowband. And most plasmonic enhancement devices are narrowband, single resonance, but I shall show that you can devise a structure in which you have a broadband enhancement, and so you can operate at two frequencies easily, and so do this mixing process, just one of many things you might do. So how do we go about that? So what we're about really is, rather than just guessing what a single device might be, what it might be like, we want to get a design paradigm so that we could, if somebody comes to us and say, well, I don't like this device you designed, can you find me another one which conforms with the particular application I have. So what we want to do is to do the design in 2 steps. First of all, we want to find a system, a mother system I'll call it, that collects light and is broadband. And ideally, we want it to be sufficiently simple that we can actually have a formula, an analytic formula that describes its function. But because we want it to be soluble in a simple manner, its geometry may not be the geometry we desire. And then we've been developing this technology of transformation optics, which tells us that if we change the geometry, how we must change the material parameters and to have this same broadband property, but in a different geometry. And so we have a whole series of daughter structures whose shape may be dramatically different from this mother structure, but which inherit if you like, the DNA, which is the broadband harvesting property. So now we have this whole family of structures with the same genes, which also inherit the analytic solution. And one of there are about 3 or 4 canonical structures. I can't describe the whole zoo which we've developed. Sorry, I shouldn't describe Dawes Autos as a zoo, should I? But anyway. So if you take this structure here, which is a thin slab of silver, and it will then sustain surface plasmons, which hybridize across here, and these surface plasmons are highly mobile. On an isolated surface, they're not, but if you have a thin slab, the surface excitations are very mobile. And so if you place a dipole here, you extract its energy into these surface modes, and the energy is carried off to infinity. Now, so that's broadband. This is a very wide spectrum. It goes right from the surface plasma frequency down to 0 frequency. It's about as broadband as you can get in a plasmonic system. And it harvests energy. But that's not what most people would call harvesting, because the energy, in fact, goes off to infinity. Mathematicians are unperturbed by infinity. And this transformation here, which is Z is a complex number, so I'm in 2 dimensions here, X and Y, and this is the usual complex number, Z, and I'm going to do an inversion. And this particular transformation takes points at the origin to points at infinity. I'm going to choose the origin here at the center of the dipole, and of course it takes points at infinity, which is where your energy is going. It maps those to the origin. So in the new structure, we have energy which is harvested here at the fat bit, which was the origin here, but now infinity becomes really small, and this is where infinity is mapped to, and so the energy, instead of going off to infinity, goes down to the origin here. And the dipole, if you invert about the center of a dipole, what you get is a uniform electric field, because the dipole is 2 very large charges close together, and if you map with an inversion, those 2 charges go to near infinity, and 2 charges at infinity produce a uniform electric field, which doesn't have to be due to 2 charges and could be produced by an incident plane wave, which is what I shall take it to be from now on. So an incident plane wave excites a plasmonic wave in this crescent light structure, which is harvested to this point here. But just as you're crushing the structure down here, so you take with it this wave, and the wavelength is crushed, and the energy density is crushed as it progresses toward this point here. And I show that in the next slide, that as you go to this point here, the energy density goes, this is a log scale, by the way, the energy density goes up to a very high value, and you can see the wavelength decreasing here. There are also other very similar structure which can give you 2 kissing cylinders, and very similar enhancements happen there. This is silver. We've included the Johnson-Christie losses, so losses are included, and the frequency is 9/10 of the surface plasma frequency. This doesn't really give you a picture of how big the enhancement is, so let me instead show this picture here, and this angle theta goes round, measures the field on the circumference of this device round from 0 degrees round to the kissing point here. So 0 degrees off here, and the kissing point is 180 degrees. And this is a plot of the electric field in the x direction. And you can see that it starts off at a low value. This is normalized to the incident field, and the enhancement of this field gets greater and greater as you squash the wavelength down, so you squash the energy density down, and so the field goes up. And this enhancement will continue until you've got an infinite density of field here. There's no reflection of this wave. It just goes on and on. And the reason it turns over is loss. This wave is going slower and slower, so it's more and more vulnerable to resistive losses in the silver, and eventually these catch up with the gain process, and it peaks out here. But the peak is an enhancement of the electric field of more than a factor of 1,000. So if you're looking at a Raman signal from a molecule, remember there's enhancement in and out. So that's the fourth power of the electric field enhancement. This would 10 to the 12th Raman enhancement in this system. Just to illustrate the variety of structures which you can take, if you now take a slightly different system in which you have now, instead of a silver waveguide, I've got a vacuum or dielectric waveguide sandwiched between two silver slabs, and I'm going to take a periodic array of dipoles, and the periodicity forces the spectrum is still broad, but in fact it's quantized, so you have a whole series of resonances in this particular structure. And if you provide this transformation here, this structure maps into two cylinders which are not touching. And you can calculate all that analytically. And what you see here is the enhancement. Actually, this is the absorption cross-section, which is a measure of the enhancement. And the absorption cross-section as a function of frequency up to the surface plasma frequency, and the y-axis is of increasing spacing between the cylinders. So obviously when the cylinders are far apart, it just looks like twice the absorption of a single cylinder at the plasma frequency. And as you bring them closer together, these resonance states peel off and eventually, at very, very small separations, fuse into a single broadband resonance. Now, one other interesting feature of this system is a hidden symmetry. So if I ask you to classify these states here on the basis that they were obtained as eigenstates of this structure here, you'd probably say, oh, well, the whole thing's a mess. These things are many high harmonics of waves going round the cylinders, and there's no particular symmetry in this other than the reflection symmetries of this system. But this system has translational symmetry. So each of these modes in this system is described by a k-vector. So you have a k-vector here, but the k-vector it can still be used to classify these states, but the symmetry is hidden. So it's a very nice thing that the transformation enables you to classify the states just as if this were a periodic block system, but it isn't. But its mother has that symmetry. So obviously, the benefit of harvesting is that it's broadband, and you can do multi-frequency experiments on it. So now you can detect a wide range of molecules with different spectra in the same system. Or we could pump the system at one frequency and amplify a weak signal at another frequency. So there are all these benefits, but things can go wrong. One thing you might think goes wrong is that silver is a little bit lossy and gold's even more lossy. And certainly that's a limitation on how much enhancement you can get. But it's not the strongest limitation. And it turns out that even with the losses, thank you, in silver, you can get very, very great enhancement. Loss is not a barrier to this functioning. But what is a barrier is the fact that you have radiative losses if the system's too big, and if the system's too small, then you have something called nonlocality, which is the fact that the electron distribution at the surface isn't precisely at the surface, it's spread out a little bit by the Fermi wavelength. And then there's the usual problems of manufacture. So I'm going to skip radiative losses, and because I have only 5 minutes and I do want to get onto this important thing. This is work by Antonio Dominguez, and what happens in the case of when the cylinders are a small radius is that the charge induced doesn't sit precisely at this interface, it's smeared out. And that means that when the waves approach one another at this point, they don't come quite as close as they do in the local model because the charge is smeared out. And whereas in the local model, the waves coming around here never get to this point, because they can't squeeze through this gap which doesn't exist. Now there's a gap there and the waves can go around. So in the local model, even when the cylinders touch, the levels are quantized because they have to phase match across this gap here. And so when you look at the absorption cross-section of a non-local system, here's the absorption cross-section versus frequency of a local system, and you see that the non-local system for various degrees of non-locality, the green one is the actual one, you get quantized levels. And finally, if you plot the enhancement factor between the two cylinders as a function of frequency and as a function of the radius of the cylinders, you see that there's a broad range here where the enhancement is very, very great. And it turns out that if you recognize that you're limited at one side by non-local effects and the other side by radiative effects, there's an ideal range for the radius of this system, which is between 35 and 80 nanometers. So if you want enhancement experiments to work well, this is the range of sizes you have to look for. So thanks to Eli's original insight, I think a great richness of exploitation of structure and its interaction with light on the scale of the wavelength and beyond, from photonic crystals into metamaterials and into plasmonics. It's been a great ride over the decades, and it's one which will continue. And so, with thanks, happy birthday, Eli.
I have a question. To what extent can we thank for some of these inspirations, not to me, but actually to Marconi? Because Marconi created something unbelievable even today, that you can communicate over long distances. And one of his tricks was to focus the energy down to a very small nonlinear element, which in those days was called a coherer.
Yes. Well, there are two ways of getting enhancements. One is which you get in a dipole aerial, you put two conductors, so you've got a uniform electric field, and you put two conductors which short circuit most of that field, and so now the voltage drop, instead of being over a meter, is over a few millimeters, and it's called voltage division. And that works, of course, but this is a different mechanism because it's actually wave guiding mechanism and concentration of waves. So although Marconi thought of many things, not only in the scientific domain, but in the inventive financial game as well, I don't think he thought of this sort of enhancement.
Excuse me. after some transformation, you came to cylinders.
Yes.
Okay. What is the difference between this solution and very old solution by Raphael Rupin for 2 spheres?
Sorry, which other solution?
Rupin.
Yeah,
Raphael
it's
Rupin.
the same.
It's
the same.
The same?
It's the same, but the point I'm making is that people have looked at these structures in the past. There's been solutions for a cone, for 2 spheres, for 2 cylinders, and so on and so forth. But the point about this approach is that you have one analytic solution, and from that you can generate a whole mass of structures. So it's the relationship between them and the ability to classify these structures with, for example, the k-vector. So what I hope I'm bringing is an insight and understanding. And individual structures have been solved by spherical harmonics and so on and so forth before. And by the way, analytics are not just an ornament. If you try solving these structures in COMSOL, because of the singularities involved, it's a very, very difficult problem. And we're struggling at the moment to look at 2 touching spheres in COMSOL. And it takes a few weeks. It's difficult.
Thomas. So, is there a fundamental physical limit to how much field enhancement you can have, something that's independent of material property?
I don't think there's anything fundamental that sort of Maxwell's equations say, thou shalt not go further than this. There are certainly materials limitations, which are chiefly due to these effects here, but they are material dependent and are not fundamental.
Well, John, thank you for
Yes, thank you.